Chapter 8 Examples of the use of FIR and IIR filters in removing noise and unwanted signals. In this chapter, some practical examples for removing noise and unwanted signals from desired signals are examined. The first one is related to 50 Hz noise removal from ECG signal. Okay. Contaminate an ECG signal with 50 Hz noise and then denoise it with two Remes and elliptic band stop filters. Make any reasonable assumptions about the passband and stopband frequencies as well as the minimum attenuation in the stopband and the maximum ripple in the passband. Consider the sampling frequency as the value reported for ECG, which is equal to 200 Hz. Results are illustrated in figure 8.1. Okay, let's have a look to the results. ECG corrupted with 50 Hz noise, the original input signal, corrupted signal by 50 Hz noise, and the output result for Remes FIR filter and for elliptic filter, both band stop filter. Okay, you see the degree of success in removing the noise. Now we are going to run the program in Python. Okay, let's run the program. The same figure. Okay, the degree for Remes is reported to be 37 and for elliptic to be equal to 4. Compare these degrees. Which one is better in your assumptions? The same code appears here. We have worked on elliptic IIR design and Remes FIR design in earlier chapters. Okay, so showing the coding very fast. Later you will have access to the code via Google Drive. Okay, reading ECG file and plotting. Here you see the details. How 50 Hz noise has been added to the signal. It just appears here. Okay, controlling the amplitude of the noise. Later you will work on it by decreasing and increasing the amplitude. And here, how to generate 50 Hz noise, how to add it as additive noise to the original signal and call it corrupted signal. Then trying to filter out, you see, stop band frequencies 45 Hz and 55 Hz. It should be enough for removing 50 Hz. Okay, what about passband frequencies 35 and 65? And think about how transition region is sharp. You should work on it. Anyhow, and then trying to filter out the corrupted signal. Okay, now take home. An important part of learning. Write the necessary code for MSE mean squared error, MAE mean absolute error, and correlation to be able to analyze the results as quantitative approach. Okay, we just show an illustration about qualitative improvement, qualitative achievement. But here you'll find the results as a number, MAE should approach to 0 as well as MSE, but correlation should approach to 100% similarity between the processed data and the original one. Okay? So this part is very important, very crucial for learning. Anyhow, second part. Add FIR filter using window-based and IIR filters using Butterworth and Chebyshev of types 1 and 2 to the denoising operation and make a comparison between the output of each of suggested filters. Okay? The third part. Modify the parameters for FPS and FSS, okay? Passband frequencies and stop band frequencies and report the results. Using MSE-MAE correlation, determine which method performs the best filtering. Measure SNR, signal to noise ratio, then increase SNR and report what happens. The next question. Considering the normal heart rate about 60 up to 90 beats per minute for a normal human being, which is equal to 1 up to 1.5 beats per second, hertz, as well as the heart rate of a child, a little bit more, and even the rapid heart rate tachycardia and slow heart rate bradycardia. 50 Hz disturbing signal will appear as a high frequency for all the cases reported. Okay? So, therefore, it is possible to use a low pass filter instead of a band stop filter we just showed. Used with the following specifications. Change the cutoff and stop band frequencies to pass band frequency being equal to 30 Hz and stop band frequency being equal to 40 Hz, and write a Python code and report the differences. Which one do you prefer? Okay? Now, plot the frequency responses of the filters too. Also, plot the spectrum of pure and corrupted ECG. And the next question, test other existing 11 leads because you have access to 12 leads. Lead 1, 2, blah, blah, AVR, AVF, up to V1, V2, up to V6, okay? Altogether 12 leads of information and try the filtering over all of them. Of course, after corruption. Try SOS, second order section option in output for IIR filters and report the quality. Again, which one do you prefer? Right. Now, 4K Hertz noise removal from audio signal. Okay? We just want to have and get confidence and work on any corrupted signal. So far, we have tried ECG signals. You may try them on EEG, EMG, anything related to biomedical engineering or audio signal engineering. Contaminate an audio signal with 4K Hz cosine and then denoise it with Remez, elliptic, bandstop filters, as well as FFT-based method. Make any reasonable assumption about the passband and stopband frequencies as well as the minimum attenuation in the stopband and the maximum repel in the passband. Consider the sampling frequency as the value reported for audio, which is equal to 22,050 Hz, about 22 kHz. Results in time and frequency domains are illustrated in figures 8.2 and 3 respectively. Let's have a look to them. Left channel, of course, is shown. The original input signal. corrupted signal, the output of Remez filter, you see how weak the quality is. What about elliptic? Somehow reasonable, okay? And this is the output for FFT based denoising method. There's a little problem here, but the rest may be assumed to be acceptable. You will judge. Anyhow, this is the spectra of the original signal, of course, amplitude, abs of x, and corrupted signal. You see here how 4K hertz is shown. The output result for REM is no reduction in noise, but acceptable operation for elliptic as well as FFT based method. Okay? Now we are going to run the program inside Python. Please listen carefully to the filtered signals. Okay? The result for a spectra, the same figure, which has been grabbed and put into lecture note. Okay? Now think about the degrees reported. The degree for Remez is 200 hertz, 200, excuse me, 200, and the result wasn't acceptable. But for elliptic, it is reported to be 4. Okay? These aspects are very important aspects of engineering. Now, having a look to the code in Python, declaration, correct length for FFT. This is somehow similar to the syntax nextpov2 of MATLAB, and of course later 2 to the power of r gathered from nextpov2. Okay, denoise based on FFT. This part is very important. Later you'll have access to it. Okay, how we have done inside FFT based method, a very huge filtering. Okay, the idea is very simple, right? Okay, let's scroll up to end of the program. Here, get computing inverse FFT after computation. This part is very crucial. Okay, you change some components in frequency or FFT based method inside FFT environment, and its complex conjugate should be modified too. That's the key point. Maybe in rare books, this idea has been reported. Please work on it in detail. Okay? Elliptic band stop filter, no problem with it. We had plenty of experience about it. And Remez as well. Okay? Plotting and playing wave file. Also, we have worked on it in earlier chapters. Okay. Getting information about the wave file. And let's do it somehow fast. Okay. Now, take home. Do similar research job related to what we just showed. Okay? Is the performance of Remes filter acceptable according to its degree and quality of frequency response? Isn't the sampling frequency of the audio signal high compared to those in the defined specification? To investigate the issue, change the frequency of the disturbing signal to the city power frequency 50 or 60 Hz and prepare a technical report. Also, prescribe a solution. What's your solution? Okay? Add FFT based method for ECG program 2 in earlier exam. Now, the next attempt 4K and 4.5 Hz noise removal from audio signal to polluted signal. We don't run it, but just we'll show the details. The same approach as earlier. Okay, contaminate an audio signal with 4K and 4.5 kHz cosine and then denoise it with Remez elliptic bandstop filters as well as FFT based method. Make any reasonable assumptions about the passband and stopband frequencies as well as the minimum attenuation in the stopband and the maximum repel in the passband. Consider the sampling frequency as the value reported for audio, which is equal to the same one. Results in time and frequency domains are illustrated in figures 4 and 5 respectively. Okay, in time domain you see just how the corrupted signal appears. Of course, again for left channel of stereo signal, and the output for REM is not acceptable, but acceptable for elliptic and FFT based method. Okay, here everything is clearly shown, illustrated. You see the component for 4 kHz and 4.5 kHz. Remez no success about removing the noise, but elliptic acceptable behavior and more acceptable for FFT base. Of course, you will judge using MAE, MSC, and correlation. MAE, MSE, and anything you have as tools to judge. Okay. Here is the code without running it inside Python because we don't have any free time, and the length of the video recording will be increased if we run it, but we'll show the details completely similar to the previous program, except for having the second component here 4.5 kHz, which we will be shown here just in a minute. Right, yes. The first one is similar, okay, up to here. The second one, you see here, the amplitude of the first one has been chosen to be 0.1 and the second one 0.2. It was completely clear inside the figure, okay? You will work on it and change the amplitudes and will report the results. And the rest is completely similar. Right. Now take home. Do similar research jobs similar to what mentioned for the previous example. Check how many single frequency components can be added to the main signal as a contaminating signal while the filtering process is still done correctly. Okay? Now the next topic. Normal noise removal from ECG signal or somehow white noise. Of course, it's color noise because the duration is limited, but it will be called white noise, having a Gaussian or normal distribution. Okay? Contaminate, pollute an ECG signal with normal distribution noise with a mean value of 0 and standard deviation of 1, and then denoise it with two remez, still remez and elliptic. We have kept them inside competition. Okay? Two remez and elliptic low pass filters. This time, low pass filters. Also, denoise employing FFT method. Make any reasonable assumptions about the passband and stopband frequencies as well as the minimum attenuation in the stopband and the maximum ripple in the passband. Consider the sampling frequency as the value reported for ECG, which is equal to 200 Hz. Results are illustrated in figure 6 from chapter 8. Okay? Original pure signal corrupted by normal noise, and the results for remez somehow acceptable this time, and for elliptic. Now we'll run the code in a minute. Okay. The same figure. Now, the degree of the filter for remez is reported to be 90, and for elliptic, low pass elliptic is 4. Right. Here you see the coding completely similar to the previous ones. But here you see how denoise based on FFT has been appeared. Somehow a little modifications compared to the previous one. Okay. Finding the absolute value and the maximum amplitude and making a thresholding. Here you see how we have made a thresholding. If the amplitude is less than a number, so put it as 0, and of course the complex conjugate, and it filters out. You know, white noise occupies all frequency components. So in total, we should have problems with it. It's impossible to remove the Gaussian noise 100%. Okay? But you just show the quality of the output inside figures. Anyhow, let's scroll up to end. And what about the pollution here? Noise amplitude has been chosen to be 0.08. You need to increase it and report which filter fails. Okay? Mu 0, sigma 1, and noise amp times mpi.random.normal of mu, sigma, and the rest of the parameters. Okay? Additive noise. Okay? Leading to corrupted signal, and then trying to remove the noise using remez and elliptic, and of course FFT based filtering. Do similar tasks defined for 50 Hz noise removal. change the amplitude, standard deviation of noise, and report what you realize. Compute SNR, of course, we need it. Design similar strategy for corrupting an audio file with normal noise. Considering that white noise has a broad band spectrum, what should be the type of FIR and IIR filters? If you are not happy with the results, search internet for more proper denoising styles. For example, try Go-Lie filter, short-term or short-time Fourier transform, wavelet-based denoising, and of course, morphological filtering. I teach SCFT, wavelet, and morphological filtering in courses called DIP, Digital Image Processing, and Advanced DSP. So here I cannot show the details because this course is titled Digital Signal Processing. Modify the program to add 50 Hz plus white noises. To corrupt the pure ECG, both of them should appear, okay? And try to denoise it. And if you are interested, try to add another types of noises. For example, baseline drift removal due to respiration of the patient, or EMG noise or muscle contraction as well. But for DSP, they are not completely necessary.